we've made it to the last lecture, and at the end of Klaus's lecture, he promised a lot of things that I will talk about, and if Klaus makes a promise, I try to keep to it. So today I'm going to talk about so the third lecture will be about scrambling, ergodicity, unitarity, and all. And indeed, I will take mostly a gravity perspective now. So this is also now more about recent work that has appeared over the last couple of years, maybe 3 years now. But before I do that, or in fact to give an overview, I want to take, maybe I'll write it here. I want to take up something that Klaus very nicely had on one of his transparencies, namely this idea of having various significant timescales from the perspective of, well, all of these words. And I want to, so this is like, let's say, and I want to say how we characterize them in a many-body system. And here I will give a sketch of what the corresponding signature at the timescale is from the perspective of the gravitational system. And today I will specialize to this ADS CFT case. So I will be talking about gravity in ADS. But actually I do want to say, generally speaking, that because quantum chaos, one of the nice things about it is that it has a great deal of universality. So I'm personally quite convinced that many of those things could be also said about flat space gravity, de Sitter gravity. It's just not clear technically how to make them precise, while in the ADS case, it is in, well, all of the examples that I choose to talk about. So the earliest timescale is something that I would call here local thermalization. And that's sort of the temperature scale associated to the time scale associated to the inverse temperature. And we've already actually understood, well, we have said what this is. This is sort of like the time scale of black hole formation. It's a very early time scale in this game. The second time scale that has come up was this quantum butterfly or scrambling time scale. So in the high energy business, we like to call it TS for scrambling. So this is the, let's call it the quantum butterfly effect. And we like to associate it to things like out of time order correlation functions of the form, let's say A, B of t, A, B of t, calculated in a thermal ensemble. Now, on the gravity side, and this is the first thing that I will explain in some more detail. This actually, well, there is a, well, we might just call it a black hole butterfly effect. And it has to do with the behavior of gravitational shock waves. And effects such as, you know, blue shift of energy, like the sort of effect of the space-time curvature on energy that can act such as to boost the perceived energy, and that can be an exponential effect, and that exponential effect can be precisely identified with the quantum Lyapunov exponent here, e to the 2 lambda t, via this ADS CFT duality. So that's the scrambling time. Then, right, so this black hole formation is essentially a classical effect. But there is, already mentioned that there is this Hawking radiation, which actually will typically lead to the black hole evaporating. But in particular, though, it's a quantum effect. And so once we go to later stages of the thermalization, we will have to start understanding quantum effects on black hole spacetime. And so the another would be something like the tailless time. This is, of course, a many-body tailless time. And we've already spent, not in these lectures, but in private conversation, quite a bit of time defining what could be a many-body tailless time. I don't have the time to get into those discussions. In fact, I think some of those are open questions, but roughly speaking, we could say this is a time scale at which we are allowed to start describing the system in terms of random matrix theory. And a big question was, until recently, how do we understand this sort of random matrix theory description for black holes? And a major development in recent years was that we actually understand this in terms of non-trivial space-time topology. And yeah, that's quite fascinating. Roughly speaking, it has to do with things like instead of just having a solution in two-dimensional gravity, which is a two-dimensional surface, we start including things which are two-dimensional surfaces that have like handles attached to them or multiple boundaries. So I will talk about this also. But finally, the last time scale that is maybe from the gravitational perspective, the most interesting one is the Heisenberg time scale. Which is the inverse of the average level spacing up to factors of pi. And this is, of course, the time scale where indeed the discreteness of the spectrum or the individual energy eigenstates start to reveal themselves. That's so interesting because it's a window on the black hole microstate spectrum. And what we could say here, I mean, okay, what's the good word? It's like very non-trivial topology. So it's in some sense, so this is like, you know, low genus, low number of handles. What we have here is some kind of, technically speaking, let me call it non-perturbative topology. And what I mean by this is that we write things as a series over, well, in two dimensions, we can say this very precisely over genus here, but there is a non-perturbative completion of this series over genus, which in some sense involves universes that have infinite genus. And in fact, we have shown that those things can be summed up and they give you information about the tailless time physics of black holes. That's what I mean by non-perturbative topology. They're sort of the non-perturbative completion of what happens at the tailless time, which of course I think is something that from the quantum chaos perspective is familiar to many of you, because that's one way of thinking about how you transition from this sort of rising ramp physics to eventually the saturation. Okay, so my plan is therefore to give you a little bit of a sketch on each of these time scales, except this one, we've already talked about this. Yeah, that's basically it. So are there questions about this? Well, in the black hole, this translates to a semi-classical calculation. But it's true that in general, in this ADS-CFT duality, think like, at least at leading semi-classical order, something like a quantum expectation value of this many-body boundary system translates into essentially a purely classical gravity calculation. Okay. And actually, one thing that I didn't say last time, I said that I was going to tell you about microscopics. There's actually one remark that I wanted to make, which is, this is for today. This is just a remark. So recall that I said that there would be these dual pairs. Actually, I want to just mention two examples. So I'm going slightly back to last lecture. So one example, so examples of dual pairs. So two theories that are dual in the sense of many body or quantum field theory and gravitational. So the one that is the most familiar to our community, but is probably very exotic from the perspective of people that are interested in also realistic systems. This is the one that was first proposed by Maldacena. This is the so-called n equals to 4. So there's a fourfold supersymmetric quantum field theory. N equals to 4, d is equal to 4. So this is in 4 space-time dimensions. Supersymmetric Yang-Mills theory. So this is a theory that has a gauge group SUN. Different from this n, this is like some calligraphic n. That's equal to 4. And this n is a parameter of the theory. It's the rank of the gauge group. And this group is supposed to be dual to a kind of string theory. And that string theory lives on ADS5. I'm being very sketchy here because it actually lives on ADS5 times some internal manifold. And we could say much more of the details of this. But the one remark that I wanted to make, because I think it will tie things a little bit together and also now has something to do with your question, is that this string theory is a quantum theory. And it is understood very well as a quantum theory, which includes actually gravitational interactions. But it also has the feature that if I take the limit of this duality that n is very, very large, so the rank of this gauge group is very, very large, then there is a semi-classical expansion of this quantum field theory, a la 't Hooft. And in this case, we actually get classical or semi-classical gravity. Okay, so this is the limit where I can do a sort of a large n saddle point approximation of the field theory. And there is some magic that happens, which is this precisely this ADS-CFT duality, which tells me that the actual saddle point equations, if I sum them up, I get actually a saddle point equation that looks like Einstein's equations. So there's a quantum field theory that has a limit, semi-classical limit where n is very, very large, and I get Einstein's equations. And what's important is that the Newton constant, which I talked about, we should think about as being 1 over n. So the bigger this rank of the gauge group, the more weakly coupled and the more semi-classical this gravitational theory behaves. Okay. All right. So that's one example. The second example, which is, yeah. Yeah, but not, now we're talking about what is the meaning of a duality. So the meaning of the duality is that they both encode the same physics, and the simple way of thinking about what is a very large n of the boundary theory is instead in terms of Einstein's equations in ADS5. In that sense, it becomes simple. Yes, but they're supposed to describe the same physics. So the second example is this one, which is this SYK type of models. That's a very different kind of large n limit, but I just wanted to write it down. Here we have a Hamiltonian, which can actually be written very simply. I mean, I should say that in the case of n equals to 4, if you wish, you can also write the Hamiltonian. Of course, it's a quantum field theory, and people prefer to think of it in terms of Lagrangian path angles and so on. But you can write down the field content of this thing. You can write down what it is, but it doesn't translate to many body physics. It doesn't translate in any known way to disorder physics and so on. And understanding this theory using those kind of methods is actually very challenging and is actually a problem of ongoing research. Here, in some sense, the many body side is something that is much more familiar to a crowd like this, because it's a system of n disordered Majorana fermions, psi I, psi j, psi k, psi l, and I sum these indices from 1 to n is now the index of sites, and there is supposed to be, this is dual to ADS2 quantum gravity. In the IR limit. That's important, actually. Okay, and so the idea is that, for example, if I take now a 4-point function of operators, which could be the elementary Majorana fermion, there is a Lyapunov exponent that can be calculated, notably was calculated by Kitaev. And there is an analogous calculation of a 2-dimensional shock wave that follows these rules of how you map from gravity to the field theory, and that gives the same Lyapunov exponent. Okay, so okay, so most of the examples of ADS-CFT dual pairs are in this class of objects, and this is a much more recent thing. But also it's a little bit puzzling to understand how you can have in lower dimensions disordered theories, and you can have in high dimensional non-disordered theories. It'll be very interesting to understand non-disordered versions of this in detail, or to understand how this can be related to a disordered type field theory. So I also in a second, I also promised to give you some maybe interesting ideas to work on. So that is, in my opinion, one of the central questions, is why these lower dimensional examples seem to behave so differently from the higher dimensional examples. And can we actually make them look more similar by thinking about them in creative ways? Yes. Well, for SYK, it is precisely actually what I drew here, because SYK is dual to a 2-dimensional theory of quantum gravity. And so a 2-dimensional theory of quantum gravity is a theory of surfaces. And so for example, the thing that gives rise to, if you're in the unitary symmetry class, linear rise of the spectral form factor is precisely a geometry which is a 2-boundary geometry, which is a non-trivial connection between two, if you want, dual universes to SYK. So this is also non-trivial topology because it's a multi-boundary thing. It turns out the unitary class, as you all know very well, is a little bit boring in that it only has like one perturbative diagram that gives a linear rise. You could also add interesting topology, for example, in the orthogonal class. And now we would really be again in this obviously interesting topology case where you have a multi-boundary surface with a handle in the middle. Okay, right. Yeah. Here, yes, but in some restricted sense, because so there is a whole industry. This predates this kind of stuff by 15, 20 years. And obviously people have been trying to understand these kind of questions previously. And so one way of understanding 1/n corrections, well, that's explicit calculation in n equals to 4 super Young mills. And there turns out to be an integrable subsector of this theory. And there are very impressive results on getting highly non-trivial quantum results using the tools of integrability. In some sense, the problem for us is a little bit that if you now concentrate on an integrable subsector, all this sort of generic quantum chaos behavior that we want is not accessible. So in principle, yes, but it's just these theories are more like QCD, which is a very difficult field theory to solve. And in practice, you would need to find the microscopic spectrum of such a theory. Right? Other questions? Okay, let's talk about scrambling. So So the idea would be to calculate something like an OTOC. And for this, let me tell you something about black holes. So there is actually canonical purification of the canonical density matrix, which is called the Sommerfeld double state, which is 1 over the square root of the canonic partition function at inverse temperature beta times. Now, what I've done is, what I will do is I'll take 2 copies of the Hilbert space, the identical Hilbert space of the quantum system that I'm interested in, and I will put it into a, in some sense, maximally entangled state. Actually, maybe in some of the lectures which also talked about multipartite entanglement, we would understand a little bit better in what class of states this falls. But the point is actually the following, is that I take the sum over the entire spectrum and I call one copy, okay, so one copy of my theory I call the left copy, and the other copy I call the right copy, and we'll see in a second why we use this terminology. So I take n left tensor n right, so the same state in the left and the right, okay, because I have the same Hamiltonian, they have the same spectrum, and I'll put them into a sum over bell pairs in some sense, but the factor is given by this Boltzmann-like factor in front. You know this, of course, I think, or many of you will know this. And one of the nice properties is precisely this purification of the canonical ensemble. So if I take, for example, a partial trace over the right or the left system of the density operator psi, then what I actually get is I get the row of beta, this beta, the actual canonical density matrix for what's left. So if I trace over the right Hilbert space, I'm left with the left system and vice versa with the right system. So it turns out that that's a convenient thing, because actually the black hole itself, the eternal black hole, the time independent solution that always has been there and always will be there, it actually encodes this state. So actually when we draw a black hole, and I want to go into a slightly more abstract way of drawing it, we have actually 2 asymptotic boundaries. We have a left boundary and we have a right boundary. And there is also singularity, which is, maybe I'll draw it like this. There's a future singularity and the past singularity. And there is this surface, the null surface, which gives us the horizon. So this is a more abstract depiction of the black hole. This is the region, purely these 2 regions here, this sort of triangle and this sort of triangle are the ones that we have seen in previous lectures. This is like the exterior of the black hole, this is the horizon, and this is the interior of the black hole. And this observer that I drew at some point would have gone in through here and hit the singularity like that, crossing the horizon there. But it turns out that the actual solution geometrically describes not one exterior region, but 2. So the right exterior region and the left exterior region. And both of them have an asymptotic ADS boundary. But what we know is that precisely though the black hole therefore encodes a state where here I have a copy of the CFT left, and here I have a copy of the same boundary system on the right. And if I think of a state, for example, that would be prepared at a slice t is equal to 0, this is the time slice t is equal to 0, it would be this state. A very highly entangled state between one copy that I call the left copy of the CFT and another copy that I call the right copy of the CFT. And in actual fact, there is a simple trick that allows me to write actually kind of any thermal expectation value in terms of something with respect to an expectation value with respect to the Sommerfeld double state. This is the same idea that if I take a partial trace, I just get the canonical density matrix. Yeah. Yeah, no, so on the level of the gravitational solution, I cannot decide, because in fact, if somebody writes down the Schwarzschild metric, and here is the ADS Schwarzschild metric, okay, then we've already encountered this idea that there are points where the coordinate system becomes singular, but they are not physical singularities of the actual solution. So what we need to do is we need to find a good way of patching coordinates so we can go through those coordinate singularities. Now, the thing that needs to be done is to find the maximal manifold that is defined actually by the solution, which means that whenever we hit some coordinate singularity, we must cure it and we must go through it. And so the maximal solution is actually this. So if you want, the Schwarzschild black hole itself has two external regions. Okay, this is of course very puzzling when you first discover it, but it's a mathematical fact. So this is, if you want, the maximal analytic continuation of the Schwarzschild solution that I wrote down. And well, it's one of the things that was appreciated after the Second World War, but I think shortly after the Second World War. It's just true. And in fact, the connection that goes from left to the right, there's like a spatial slice that really connects these two boundaries. This is the thing that people refer to as the Einstein-Rosen bridge. It's some sort of slice that connects two actually otherwise disconnected universes. So if you, it's another one of those weird properties of black holes, but here, just for the sake of being complete, it's a property of these static solutions. It's not a generic property of black holes that form from collapse. But these static solutions that you can just write down analytically, they have this property, okay? And the interpretation of this property in terms of the field theory is that in fact, they encode a particular state, and this state is this one here. So in some sense, no, you don't have the choice. Okay, so now the idea is that this thing can be written now as an expectation value in a perturbed version of this Sommerfeld double state. It's actually like a quantum interference experiment. So here, if we now really thought of how might we do this quantum mechanically, even perhaps in the lab, not with black holes, but if you want to measure OTOCs, you might want to have two copies of the system. You perturb one system, and then you measure, and the other copy you measure, and then you perturb, and then you look at their overlap. Okay, this is exactly what we will do here. So we have like a perturbed version of the Sommerfeld double. Then we take a copy of the operator A, which we act on the left Hilbert space. We take a copy of the operator A, which we act on the right Hilbert space, and we take this overlap. Now, yes, I don't really have time because I want to get to other timescales, and I'm already halfway through my own timescale. To do this calculation in detail, it's a few lines calculation to show it. But for those of you that have worked in OTOCs, I do want to say that what you get out of this is this OTOC, which is regulated. So where you take the canonical density matrix, you chop it into 4 parts, and you put one in between each pair of operators. So this is the regulated OTOC, if you want. Okay. And now, okay, so now what one needs to do is one needs to understand what this thing means here. So and this comes with the time t. Perturbation of the state is done at the early time t before I measure ALAR at time 0, let's say. Okay, so this time t is this time here. So let me just show you in pictures what happens. What happens is that, roughly speaking, okay, so we want to measure A left, A right at time 0. If I didn't perturb the Sommerfeld double state, a good measure for this correlation would be the length of this geodesic from left to right. Now, you're not supposed to say, that's obvious, but it is a calculation that can be done. And a good measure, it's an approximation calculation exact, but I want to give you pictures. So the length of the geodesic that connects these two boundary points through this Einstein-Rosen bridge is a good measure for the correlation in the unperturbed thermal field double state. But what I want to understand what is the length of this geodesic, therefore this correlation function in the perturbed thermal field double state. And what happens is that in some sense here at some early time, so this is now the time t, I release some kind of energy pulse. Okay, I can explain this with what I said last time in a second. And I actually have, you see, because time, the property, I already said this sometime last time, but the property is also that time here goes like this and here it goes like that. That's again a property of this maximal analytic continuation of the manifold. So early time t is inserted here, and if I look at the conjugate state, I'm here. Okay, but what this happens is that this releases like a small pulse of energy, because remember what I said, the correspondence between operators and the bulk is that the operators are like sources for bulk fields. So I put a small source for a bulk field here, and it will propagate into this black hole. But if I do this early enough, and early enough will mean around the scrambling time, actually what we should be thinking of is now a 2-to-2 scattering process through the bulk. I have some pulse that is released here, I have some pulse that is released there. I want to ask what happens if I measure here and there. And what that means, it's now a 2-to-2 scattering process with a center of mass energy here, which is actually enormous, because effectively moving into the bulk is like boosting into a highly boosted frame. And what that will do is it will strongly modify this whole picture. So instead of having this picture now, so actually in the presence of these operators, this is not the correct picture, okay? I just motivated that. The correct picture to calculate this 2-to-2 scattering is that what will happen is that this will effectively become a shock wave of extremely high energy that will distort strongly the horizon. And it looks like this. It looks like, let me start. Actually, I'll need a little bit more space. And right, so you get, let's keep this horizon the way it was. Now this guy will be strongly curved, and the horizon hits somewhere here, and this guy will look like this, and then I still have my singularities. Okay. They also change color. Okay, and so now I basically have inserted my operator B here. This has basically moved parallel to the horizon, but has very much changed the geometry. And here is its conjugate B. And now what I want to measure is the operator A left, A right, but the geodesic has now been stretched by this factor here. So instead of going in, it will go in. It will in some sense be, now I'm just talking intuitively, that the space-time geometry is deformed. That's what happens. But you can say it will be dragged along by this shock, and it will come out here. And the geodesic will be much larger by this amount. And this amount you can calculate. It's just the blue shift factor of the black hole. And this amount is like, I could characterize it by the center of mass energy. So E center of mass is like E released here times E to the 2 pi times the time at which it's released divided by beta. That's a fact of this geometry. And you all, of course, recognize this. This is the maximal Lyapunov exponent. And so then if you compare the size of this geodesic to the size of this geodesic, that gives you the scrambling behavior. And so therefore, this geodesic goes like e to the 2 lambda, let's call it black hole, times t, where lambda black hole is equal to 2 pi over beta. Okay? So that's how we think of the quantum butterfly effect in gravity. Yes, sure. Yeah. Yeah, I think that's a very good question. So in general now, the way that you do this is that you say you can classify the operators by the best way of doing it is in some sense by how they decompose under the symmetry groups of the theory. So you can identify particular operators in the boundary system with particular fields in the bulk by symmetry. So we know what fields are dual to the simple operators in the field theory. However, it is important that we take simple operators, things like, for example, that would be individual Majorana fermions. If we take extremely complicated operators like words made of the Majoranas that are of size n, I wouldn't know how to do this calculation. And I think that's probably also okay from the point of view of our understanding of many-body chaos, is if you make those operators extremely complicated, you know, they already are scrambled in some sense. So there's no scrambling left to be done. But in general, this map from boundary operator to bulk field is well understood, but it needs technology. In particular, it needs technology of understanding conformal representations, which I certainly don't have the time to develop, but it's on the level of that. Yeah. Yes, there is a 1 over n, or 1 over n squared. So it's good I actually did that detail. Yeah, that's precisely what happens. So this is the many-body h bar, 1 over n. 1 over n squared at this level. I mean, those geometries, well, Euclidean versions of those geometries are known to exist. These are multi-boundary wormholes. This is like a Lorentzian version. So there's Lorentzian time here. I'm not aware, but yeah, it's an interesting question, which goes in a different direction, namely, what kind of entanglement can still be faithfully represented by classical geometries? Because in general, not every field theory state will have a nice classical representation, because actually we're talking about a quantum theory of gravity. And so most of the states in the Hilbert space will not actually correspond to nice classical configurations. And I think it's not clear right now to me off the top of my head that there is like a tripled version of this, but I do know of Euclidean cases, which I can talk to you about later. Yeah. Well, but it's so, yes, but like that, it doesn't really make sense. Maybe that's why you're asking the question. But the problem is that you need to have a center of mass proper energy, and for this you need this view of the 4-particle scattering. And the scattering happens in a frame here. So those 2 particles, they're highly relatively boosted, and that's why they actually can change the geometry here. Because if you just send a single particle, let it fall into the black hole, it would do nothing to the horizon. It just follows its geodesic. Right? Yeah. No, it's a necessity, but the issue is very interesting. So you can, for example, you can write down many states that have the same amount of entanglement, but that have a different structure. Like you can use your unitary rotations, for example. And most of those states do not have a nice geometric smooth dual. They will be highly singular or nasty kind of quantum gravitational states, which are much more difficult to understand. If I may, Wood, for example, we are finishing a paper in which we talk about complexity of states and how it evolves as a function of time. And you explore some of this, although we do it in lower dimensions where things are nicer than in higher dimensions. But yes, you can, there are some geometric notions that you can associate to other kind of entangled states. Okay, and I believe that Wood might talk about it during this conference. Okay, now let me move on because we're still stuck at some very early time scale. So let me, okay, and I should of course say, I mean, one reason I'm keen to work to move to lighter timescales is that I've worked mostly on these timescales. So this calculation was done by Steve Schenker and Douglas Stanford first, not by me. Okay, so very good. So I was going to say in somewhat more detail now why thinking about these timescales is so important in black hole physics. I don't have the time anymore, but I do want to make one remark, which is that this is an important ingredient. If we look at something like a two-point function of simple operators, or what we actually like better nowadays in gravity, the spectral form factor, and let me call that f of t. F of t, something like will be the sum over the Hilbert space of e to the minus beta ei plus ej plus I times t ei minus ej, which we can at the same time think of as the partition function at zeta z plus of beta plus it times the analytic continuation to beta minus it. This object, that is the spectral form factor that is well known to the quantum chaos community. And if I look at log plot of this spectral form factor, something like this, what I typically find is I find some initial behavior, which most of the quantum chaos people find boring. From the gravity perspective, it's actually not so boring, but it decays, and then I'm averaging it, by the way, so I'm looking at some average behavior of this guy. So I will not really emphasize very much the fluctuations which are present. Then I have some rise, and I have some eventual plateau behavior. So it is a necessity that this thing in a finite quantum system, remember that the dimension of the black hole Hilbert space was finite, is at least on average of order e to the minus s at late times, and not zero. It cannot be exactly zero. However, by just using our semi-classical gravity prescription to calculate this partition function and its complex conjugate, find the behavior that the thing starts like we want, but then just goes to zero. So this is like, one might call this, if you want, in honor of Hawking, one might call this the Hawking spectral form factor, which I don't think has ever been used. I think this has been written on the blackboard. Well, what I mean is like using the semi-classical approximation, the same way that he calculated the temperature of a black hole. And that thing looks very good at the beginning and looks like you know, a boundary calculation that you might do. But starting at approximately the tauless time, this thing becomes just inconsistent with unitarity. And this is one kind of, let's say, very concrete way of formulating the so-called black hole information paradox. Why it's the black hole information paradox, let me not go so much into this, but the point is that there is an incompatibility with unitarity of the behavior of a semi-classical black hole. And here the incompatibility with unitarity is that there seem to be no quantum fluctuations left at late times, which if you average go about e to the minus s, okay? And this is forbidden by unitarity. So one motivation, therefore, to study how can we actually recover this mismatch here of the curve at late times from a gravitational calculation is literally in order to address these kind of unitarity problems that have been known to exist in semi-classical gravity for decades. Okay, so are there questions? I went over this really rather quickly. Okay. So, so our goal, so in some sense, the goal of this program would be, one way to say it is that semi-classical gravity only gives an averaged continuous approximation to the spectral density. Rho of E. And if you have this continuous rho of E, then very generally, this will decay to zero. What instead we want is, we want to recover rho of E explicitly as a sum of delta functions. Meaning the discrete microspace of the black hole. And actually, let me call this D, the Hilbert space dimension, which is not necessarily N, of course. So, okay, so we can try and ask how do we actually get a correction to the spectral form factor at let's say the tau time scale. So for this, let me remind you that so some of the simplest and most well understood things that are calculable in ADS-CFT are partition functions. And they are also, of course, low point functions of operators. So this was the path integral with certain boundary conditions. This was the path integral with certain boundary conditions that correspond to the insertion of sources. Let's focus for now on this guy. So what I was explaining was that a temperature beta in gravity means that the Euclidean time direction needs to be periodic. So what I should do is I should somehow calculate the sum and the integral over metrics of all spacetimes, so all asymptotically ADS spacetimes, that have that asymptote to something like a circle, a thermal circle, times maybe some other compact manifold that my gravitational solution lives on. But this is Euclidean time periodicity. Okay, so I give boundary conditions to a problem of solving the gravitational equations, and of course, subject to those boundary conditions, I must sum over all compatible spacetimes. So, for example, the simplest case of two-dimensional gravity, this can be again. This can be summarized by saying that I draw this boundary circle, which has periodicity beta, and in 2 dimensions, there's really just a circle. That's why this is particularly easy to draw. I don't have any more geometry here. In my n equals to 4 super Yang-Mills theory, I would have like S1 times S2. This would be an A2. And I need asymptotic geometry S1 times S2, which I wouldn't know how to draw nicely. And so what I should do is I should find, so this is now a circle. The boundary is really just the time circle, nothing else. So what is the bulk geometry? Well, it will be the interior of this. It will be like the filled disk, the disk whose boundary is that circle. So however, the way that this is being drawn, because later it will lend itself more to a representation in terms of Riemann surfaces, that I sort of blow this disk out a little bit like a soap bubble, and I add this guy. So in 2 dimensions, I should have said Z of beta is equal to the integral over all compatible metrics with this boundary, and just the disk topology. But nobody's to stop here, because we said that what we want is we want a solution that is asymptotically a circle. But I can draw another solution easily that is asymptotically a circle that has an infilling surface. But let us now add to this surface a handle. So I have like a genus 1 contribution, and in fact, the genus weighting factor is some coupling constant, which for historical reasons is called e to the minus S0, and in the SYK context can be associated with the extensive ground state entropy, the extensive low energy of SYK, plus e to the minus Euler character of the surface times S0 times any sort of complicated Riemann surface with one boundary, one asymptotic boundary, and let's say n handles. So this should be genus 1, and this is something like genus K. Okay, well, that as such is not yet so interesting. I think it's a beautiful mathematical fact, but it's not yet that interesting, because it becomes interesting when we ask about this object, the something that is like the Laplace transform of a two-level correlation function. So for this, I want to calculate something like z of beta 1, z of beta 2. And because this will be very confusing in a second, I want to write that I'm calculating this in 2D gravity. Okay. So what I find here is now I find myself faced with a problem where I draw two circles. I draw a circle which is beta 1 and draw a circle which is beta 2. And I ask, what is the infilling solution? Well, one class of solutions is easy. You just take any pair of these and you multiply them. So I could also multiply one which has no genus with one that has a complicated genus and so on. The point is that they are two disconnected spacetimes. These spacetimes have no geometric connections of the kind that we drew here. However, two-dimensional gravity is kind enough to provide solutions. These are configurations that exist, which, however, aren't products of two of these. Instead, they are connected to each other. Okay, so the big difference between this kind of solution and this solution is that this always factorizes into a product of z of beta 1 times z of beta 2, and this thing does not factorize in into such a product. And because people like sort of science fiction terminology, and also because it's true in this case, I mean, what this is a two-boundary wormhole. Because you have, in principle, two disconnected universes, but there exist configurations in which they are now connected, but only by going through this extra dimension in the above. And so this two-boundary wormhole is, on the one hand, very puzzling, because one might not have expected such a contribution a priori, but it is extremely handy, because what it does is it actually gives us, at least in the unitary class, the simplest thing, it's transform into the time domain gives us an exactly linear rise of the spectral form factor. So the linear rise of the spectral form factor comes from non-trivial space-time topology in this way. Now, to finish, because I think I have about 5 more minutes or so. Again, in terms of interesting problems, of course, this is well understood for the unitary class. For other symmetry classes, this gets much more complicated, as it does in semi-classics. And it's certainly an interesting open problem, but which I know people in the audience are working on to try and capture how this works in other symmetry classes geometrically. Yeah, go ahead. Well, I mean, there is one way of understanding it more, I think, at least for me, of understanding it in a more controlled setup, which is with Alex Altland, we thought about this from the perspective of the chaotic sigma model. And the way that we think about the chaotic sigma model is in terms of some symmetry breaking principle. And this symmetry breaking principle, once it's realized, it basically generates this as a perturbation theory. Now, the point is that one wants to show, and we did show, that this symmetry breaking principle can be realized at the level of JT gravity, or in fact, well, now we need to get a little bit into more complicated things. JT gravity has a non-perturbative completion, which is known as Kodaira-Spencer theory. And this Kodaira-Spencer theory can be shown to contain precisely the same symmetry breaking saddle points, and therefore the exact same sigma model as, for example, the boundary SYK type theory. And you can actually, you can associate diagrams in one with diagrams in the other, where the diagrams on the gravity side are these kind of multi-boundary one-holes. But otherwise, I think it's sort of also legitimate to say that people have accumulated a lot of evidence that this works correctly, and are still accumulating more evidence that this works correctly. I don't know, maybe you want to comment on this as well? But the matrix model, to me, you assume that there is this matrix model. Yeah. Yes. Well, sorry, I shouldn't say the wrong thing. You don't assume that there is a matrix model, but you don't have an underlying macroscopics. So it is true that Saad, Schenker, and Stanford managed to rewrite path integral of 2D JT gravity as a matrix model. And there, then the direction is the connection is direct. The problem is that it doesn't work at the non-perturbative level here, because the matrix model itself may have non-perturbative completion, but it's not clear how to associate it with the JT path integral. For this, you have to go to this Kodaira-Spencer theory. And then in the Kodaira-Spencer theory, in my opinion, anyway, the most convenient way of thinking about it is what I wrote down with Alex Altland, and I should also say with the Amsterdam group. So with Eric Verlinde, with Boris Post, and Jeremy van der Hagen. Yeah, sorry, there was another question somewhere. Yeah, Jorge, yeah. Yes, yes, there is a simple way of saying it, which is that the way to think about orthogonal group is that these are orientable two-dimensional Riemann surfaces. And if you are in the orthogonal symmetry class, you are also supposed to sum over non-orientable Riemann surfaces. And non-orientable Riemann surfaces leave room for a sort of an intermediate result, an intermediate time thing where you insert on this Riemann surface something that's called a cross cap. This cross cap is something like half a genus. And as is actually true in the unitary ensemble, all of the higher order corrections would vanish. But in the orthogonal ensemble, you now have additional diagrams which correspond to non-orientable surface which don't vanish. And in particular, they give the leading corrections which were known. And for example, give this Sieber-Richter correction, for example. It's partially understood how to get this correction. Okay, so let me finish up then with maybe 5 minutes. All right, so what we have understood now here, so this thing comes from comes from, let's say, I'm struggling with what word to put here. Let me call it non-perturbative topology. No, this is what I called it here. Okay, there's a problem actually. There's a problem because the thing is, this is already non-perturbative, and this is what we call doubly non-perturbative. But let's not bother. So let me just call this thing here topology as I did before. Topology. But I do want to emphasize that in a coupling constant sense for quantum gravity, these are already non-perturbative effects. They are not in the matrix model, for example. They're perturbative in the matrix model, and that's why there is this doubly non-perturbative business going on. So, to finish, maybe I will just say it again here on this sketch here. Question still remains: how do you get to this? So now we are at the Taoist time scale, and we have understood something about non-trivial topology of the gravitational theory. How do we understand this thing that in our world people love to call the plateau, but basically just the asymptotic behavior of the spectral form factor? And for this, in principle, well, the one recipe would be, for example, to try and resum this series and try to get the non-perturbative content of this series. So this is non-perturbative in e to the minus s, which is why people call it doubly non-perturbative, at some kind of resurgent resummation of this. That might still be successful, but the way that we thought about it was that we actually formulated this non-perturbatively defined sigma model. So we take this many-body version. We look at the many-body version of this Yefetov-Wegener sigma model, or maybe Wegener-Yefetov. And one nice ingredient here is indeed to be very explicit about how this is an effective field theory of asymmetry breaking, of in the simplest case, that is the unitary ensemble, something like SU2/2 breaking to, so this is the algebra, SU1 times 1 times SU1 times 1. And the point is that that can be explicitly implemented on the Kodaira-Spencer theory. It has been understood already previously how to implement this on the SYK side. And what we find is that we find a second saddle point of this. So the first saddle point basically reproduces this whole expansion. So in this context, we refer to this ramp here as the standard saddle point. But we get a second saddle point, which then at this time scale here, at this Altshuler-Andreev saddle point. Which kicks in around the Heisenberg time, T Heisenberg, and generates a second perturbative expansion. But where now I have a prefactor, which is which adds a phase, and I essentially get sine kernel-like behavior here. But from the perspective of the quantum gravitational theory, I do want to say these words, even though they may not be super meaningful for you now. The point is that this second saddle point is a non-trivial so-called topological D-brane of the Kodaira-Spencer theory. Now, so I know that this will not say much to those of you who don't work in the subject, but what it is simply a geometric way of understanding the topological content of two-dimensional gravity. Okay, and what is really fascinating is that this this topological D-brane, I mean, people had been writing them down previously in topological string theory, mainly because they were interested for mathematical reasons in the non-perturbative structure of these theories. And they would call this thing like quantum space-time geometry. Those are beautiful works, very powerful technology. But what was never appreciated is that those are precisely the same structures that arise in the unitarization of the quantum chaotic behavior of many body disordered systems. And so that has really opened, I think, a whole field where basically a way of thinking about lower dimensional quantum gravity in terms of matrix models and maybe generalizations actually now directly interacts with the way that the quantum chaos community has been thinking about matrix models. And I think that there is a lot to be explored in this field. Well, in lower dimensions, these are beautiful mathematical results, which I think we should certainly explore. But just to end on the challenge is that it seemed clear from quantum chaotic universality. There was the chalk. Wow, I just breathed in the chalk. Excuse me. It seems clear from quantum chaotic universality that all those things also have a realization in higher dimensional field theories that are sufficiently chaotic. I don't think that this is very well understood even on this side, but that would be the big goal. Develop it on this side and use it in the same way to solve like problems about actually higher dimensional black holes, which approach much more the black holes that live in our universe. So this is for me, the core problem is to make this work for higher dimensional chaotic field theories. Okay, and if any of you have ideas, I'd be happy to hear about it. But I think that this brings me to the end of my lectures. So I thank you for your attention, and of course I'm open for questions. Thanks. Yeah. Barry's diagonal approximation. Yes. Yes. Yeah. So are you talking about the connected form factor, or are you adding the disconnected? I'm just asking that sort of to be clear that we're on the same. No, you pick up on something important, which is that I don't think that Hawking does. So what actually, that's why I was maybe should have said it here. The early time Hawking type decay is purely the disconnected part. So this is very early physics, but I actually have some ideas of how to think about the pre-Taoist time. Yeah, which is actually kind of compatible with what the words you used, like in terms of maybe hydrodynamic modes. Yeah. Yeah. I know this Derrida model, I think. Yeah. This Derrida model, I think I know. Yeah. Mhm. Yeah, I mean, certainly on the level of methods, there is a huge amount of cross-fertilization. Actually, since Jorge is making a comment, I should have another thing that is really, again, a challenge for young people who might want to work in this field. But Jorge has also told me that, you know, and Laura have some ideas on this, but I told you, and I did say this explicitly, that I'm looking at the average behavior, but of course, even the black hole will in fact start fluctuating quite wildly around this. So the actual signal of a given black hole will not be given by the smooth spectral form factor, but this is only sort of an envelope function of the noise. And to characterize the noisy contribution, but from a quantum geometry point of view, is an outstanding challenge, and one that's very important also for reasons that maybe I can discuss in private. Essentially because if you want to go to higher dimensions, you're going to have to confront the fact that in higher dimensions, we don't have these disordered models. So there isn't really much space for averaging. Yeah. I believe it is not at very late times, yes. Okay. Thanks again.